All right, today we are going to talk about exponential growth and decay. Exponential growth and decay. And exponential growth can be modeled by the function y is equal to a times b to the x power, where a is greater than 0 and b is greater than 1. The base b is the growth factor. Which equals 1 plus the percent rate. All right, exponential growth can be modeled by the function y is equal to a times b raised to the x power, where a is greater than 0 and b is greater than 1. The base b is the growth factor, which equals 1 plus, this part's real important, which equals 1 plus the percent rate of change expressed as a decimal. All right, so here's the algebra terminology of this exponential growth. If your y is equal to a times b raised to the x power, your a, this value right here, this is your initial amount. Your b, as we just said, this is the base. Greater than 1. And it is the growth factor. your exponent. That represents your time. Or how often compounded. All right, so let's put this to use a little bit here. What you're doing with this formula is you're evaluating how much money or income or sales dollars that could be generated over an amount of time based on you being paid either interest or your money growing at a certain rate. Okay? When people put money in the bank, they like to know how much money they're going to have after a year or 5 years or 10 years based on the interest rate that the bank is paying. If somebody invests in a stock in the stock market or in a mutual fund, they invest an initial amount, okay? And they expect growth of their money, all right? And that's this growth factor. And as that money grows over time, that's your exponent, all right? What this function does is it allows you to determine how much money you're going to have after a certain amount of time based on these other variables, okay? So we're going to say here that it's a little bit of writing on this problem. Since 2005, the amount of money spent at restaurants has increased about 7% each year. All right, and each year is also means annually. In 2005, about 30 billion about 360 billion was spent at restaurants. Question is, if the trend continues, about how much will be spent in 2015? So here's the question. If this trend continues, how much will be spent in 2015? All right, so we're going to use this function that y is equal to a times b raised to the x power all right, and our x in this case, that's going to be number of years since 05. Our y is going to represent the money spent in billions. Our a, which we said was our initial amount. The initial amount spent what we're going to be using in this case is this 360 billion because that's our baseline. All right, and our B, that's our growth factor. All right, and like we said, it is going to be 1 plus. That's the key right there. It's always when you're dealing with a growth factor, your growth factor, your B, is always 1 plus your rate. Now, your rate expressed as a decimal. This 7% expressed as a decimal is 0.07. All right, that's your growth factor. 1 plus your percentage rate as a decimal. All right, so now we can substitute. We can say that y is equal to our a, which is 360, times b, which is your growth rate, 1.07. And it's going to be raised to the number of years since 05. Well, if we're looking for this trend to continue, we're trying to find out how much will be spent in 2015. Well, that's 10 years from 2005. So our exponent here is going to be 10. All right, so now with your calculator, you can evaluate this function. All right. Now, with the calculators you're using, I'm going to take my 1.07 to the 10th power first. All right. So our y is going to be equal to 1.07 y to the x. You can use the y to the x button to raise that to the 10th power. All right, we get 1.97 and push times 360, and we get 708.17. All right, so if this trend continues, how much will be spent in 2015? Well, that would be $708 billion. Correct, equals, and then push times 360 equals 708, like 708.17. Okay, perfect. Now, if you want to do it in the order that it's written here, let's see what happens. If you type 360 times 1.07 raised to the 10th and hit equals. Actually, the calculator is smarter enough to do the exponent for you. So you can type it in just how it sits right here. 360 times 1.07 y to the x, 10, and hit equals, and you're still going to get 708.17. So either way you type it in, you're going to get 708 billion. That make sense? All right. Initial amount times your growth factor. The whole key to the growth factor, and this is where mistakes get made. The key to the growth factor is that you write 1 plus your growth factor as a decimal. All right. I see it happen every year is the growth factor in this case with a 7% increase. People write 1.7 all the time. All right. 7% is 0.07. All right. 7% is 0.07. So make sure that when you're adding your growth rate to 1, that you're expressing your interest rate, your percentage, as a decimal. Got it? Express the percentage as a decimal when you add it to the 1. All right, so let's take a look at this again. Let's say that in 85, in 1985, there were 285. We're going to call them cell phone subscribers in a small town. The number of subscribers increased by 7. Oh my goodness. Subscribers increased by 75% each year. After 85. How many cell phone subscribers were in the small town in 1994 if this growth continues? This is going to be interesting. So we go back to our y equals a, which is our initial amount, times our growth rate raised to the amount of time. Okay. So let's deal with our x first. In this case, we're looking for our number of years. All right. If we're going from 85 to 1994, how many years do we got there? Nice job, guys. Good. That's 9. That's 9. Your y is going to be equal to your cell phone subscribers, your number of cell phone subscribers. All right. Your a, that's your initial amount. What was the initial amount? 285. Good. That was your initial. And your B, that was your growth rate, right? So that's going to be 1 plus. What's 75% as a decimal? Very good, 0.75. All right, this is our growth rate. This is going to be a huge increase, isn't it? All right. So our Y is going to be equal to 285 times 1.75 raised to the 9th power. All right, so here we go. 285 times 1.75 raised to the 9th power equals 43,871.99. So 43,872. Gives you an idea of what a growth rate of 75% will do to an initial amount of 285 subscribers. Could you imagine growing your business in 9 years from 285 clients to 43,872? Can you even imagine that? Can you imagine growing your money, investing $285, and 9 years later having $43,872? That's what 75% growth rate does to the number of subscribers or to an investment. That is astronomical growth. 75% each year. Boy, if our lawn business could grow like that, I could really retire in 9 years. I don't know how in the world we would cut 43,000 yards a year. Because when you have 43,000 yards to cut, you don't cut 43,000 a year, do you? You cut 43,000 every week. We have 300 right now. And in the summer, our guys cut 300 yards a week. That's a lot of yards. You imagine walking that edger around 300 yards per week? That's 60 houses a day. And then you go home on Saturday and Sunday, and then you come back on Monday, and you know what you do? You do it again to the same houses. Boy, though, the monetary difference. Whew, boy. That's interesting. That's a large amount of growth. That's why the cell phone company's got all the money. All right, moving right along here. That's a lot of growth. All right, we're going to say that when a bank pays interest on both the principal and the interest the bank is paying compound interest. All right, that means like when you put some money in the bank, if you put $100 in the bank, at the end of the month, the bank's going to give you some interest. Okay? If they give you $1 worth of interest, or if they give you $10 worth of interest, all right? So let's say you got month one. Month one, all right, you put in 100. Interest, all right, they give you $10. Now you've got $110, right? Well, what they do the next month is they pay you interest on your $110. Okay? And when they do that, maybe the next month you get $11. And then you add the 11 to the 110, so you got 121. The next month they pay you interest on 121. When they do that, that's called, they are paying compound interest. Okay? They're paying compound interest. That's different than just old simple interest. All right, we're going to say that compound interest is an example of exponential growth. All right. You can use the following formula to find the balance of an account. That earns compound interest. All right, so we've got A equals capital P left parenthesis. We got 1 plus R over N. Lowercase r over lowercase n. Close parenthesis. Raised to the lowercase n times t power. All right, now we're going to define these variables. Our A is the balance. That's how much money you got. P, that's the principal. Y'all know what the principal is? Yeah. This way? Sorry about it. Better? All right, A represents the balance. P represents the principal. That's the initial amount of money you put in the bank. Your R, lowercase r. That's your annual interest. As a decimal. Your lowercase n. That's number of times interest is compounded annually. T is your time in years. All right, so here's what we got. Let's say, suppose you deposit $2,000 in an account paying 4.5%, compounded quarterly. What will the balance be after 18 years? Quarterly. What does that mean? Anybody know what that means, quarterly? Like how many quarters are in a dollar, right? 4 quarters in a dollar. So if they compound it quarterly, they're going to compound it 4 times a year, right? Compounded quarterly means they're going to pay it 4 times a year. So here is our formula. We're going to say that A, the amount that this account's going to be worth, the amount. Principal balance, that's your $2,000 that you put in the bank. 1 plus annual interest rate as a decimal. Annual interest rate as a decimal, 4.5% as a decimal. That's 0.045 over, what's our N? Number of times interest is compounded annually. So what does that go over if it's compounded quarterly? Very good. That goes over 4. All right. Now, our exponent here, number of times the interest is compounded annually. If they're compounding quarterly, our n is going to be a 4 because it's going to happen 4 times a year. Number of years, our t is time in years, and in this case, we're talking about 18 years. All right, so there's your setup. Now, let's clean this up. All right. Our amount is going to be 2,000 times. In your calculator, we got 1 plus 0.045 divided by 4. 0.045 divided by 4. Let's go second fix 4. All right, so take that plus 1. We got 1.0113. And I got that by taking, I did this sum right here backwards. I did 0.045 divided by 4 equals, and then I just pushed plus 1. All right, and then our exponent is 4 times 18, which is 72. All right, so when you type this into your calculator, go ahead and use this left parenthesis. All right, use that left parenthesis. So let's see what we got here. We got 2,000 times 1.0113 raised 72, 4491. 4491.49. All right, so this big $2,000 that you put in the bank 18 years ago. Oh my Lord. That money sat in the bank for 18 years at 4.5%. And this is what you had after 18 years. Would y'all be happy with that? Don't say that. In 18 years of your life, all you did was double your money? I hope you wouldn't be happy with that.
So how do you put in the calculator again? I keep on doing the 0.045 divided by 4 plus 1, and I get like 1011111.
Is there a decimal in there though?
Yeah.
Yep. Well, you could do that again and then raise that to the 72nd and times it by 2,000. The other thing that you can do is you can go right here. And let's try this. I'm on second fix 4 right now. What are you on? Do you know? Push second fix 4. You should have 4 zeros to the right of your decimal. You got a TI-30XA? Push the green button, push the period button below the 2, and then push a 4. Now that's second fix 4. You got 0.0000. All right, so let's try 2,000. Push times left parenthesis the 1.0113 right parenthesis, y to the x, 72. You got 4491 now? Okay. So that works. And what you can do now that you know what the correct answer is, you can experiment it without the parentheses. You may not need the parentheses. All right. You might just be able to type 2000 times 10113 raised to the 72nd. Let's try it. 2000 times 10113 raised to the 72nd equals, yeah, you get a completely different number. So that means you need to use the parentheses. All right. If you don't use the parentheses, what it's going to do is it's going to multiply this 2000 times this, what's in here, and it's going to raise that amount to the 72nd power. But you don't want that. You just want the quantity in the parentheses raised to the 72nd power. All right. So any questions on either of those? Either of those examples of exponential growth? All right. Here's your assignment today. I got a handout for you. And I need you to keep this handout for the rest of the week. Page, you e-learners, I haven't uploaded it. As soon as I finish here and pass these papers out, I will upload this handout to the resources tab. But it's going to be page 464 today. Page 464, we're going to do problems 9 through 22. All right, if you want credit for the assignment, you're going to have to show all your work. All right, you're going to put the assignment in the basket, put in basket. Or you're going to email a picture. Got it? All right, that's your assignment for today right there. Page 464, 9 through 22, you got to show all your work if you want credit. If you're in class, you're going to put it in the basket when the bell rings. If you're an e-learner, you're going to email me a picture of it when it's 100% complete. If you don't have any questions at this time, you're excused from the Zoom meeting. And I'm going to stop this recording.